All right, hi guys, welcome back to module 10. So in this module and in the couple of the future modules, what we're going to cover is basically exercises. So if you haven't already watched all the previous modules, we go through mainly the theories. We showed you the functions of different libraries. We showed you how to import data, how to read data, and how to plot and etc. So in this exercise or in this module, what we're going to do is we're going to try to apply our knowledge in an exercise called signal noise reduction. So in this exercise, we're going to try to import some data, we're going to analyze the data, and also we're going to try to apply some filtering, or we're going to manipulate the data, and then finally plot it. So what is this signal noise reduction exercise that we're going to do today? First, what we're doing is we're going to try to create a signal, and then afterwards we're going to try to filter the signal, and then at the end we're going to plot the before and after to see what has happened to the signal based on the filter or based on what we have done to the signal. So the first thing that you can do with this exercise is try to create a data set or try to create a signal by yourself. So this can be done two ways. Either you create a synthetic signal, and this is what this line here is doing. So we're trying to create a synthetic signal that will resemble a sine curve. Or you can also use online data sets. Maybe you have an online website or another data set that has a signal of its own, and you can import that into this exercise. But for simplicity, we're going to create a synthetic signal in this module. Afterwards, after you have created this signal, what we want you to do is try to import and read the data, and then try to plot the signal or the noisy signal. And then afterwards, you will need to choose a processing method of the signal. Okay, so some tips that you want to consider for this module is try to think what kind of filter that you want to use. Maybe you can use a moving average filter. In this case, that will involve convolution, which is using the NumPy library, which is np.convolve. Afterwards, you can use a moving average filter that will smooth the data points, and then it will reduce the amount of the noise in the signal. And then you can apply the filter and then plot the before and after to see what has been changed on the signal. So before we go through the solutions, I recommend you guys to try it by yourself, and then afterwards we can discuss on a proposed way on how to do it. So good luck. All right, welcome back. I hope you were able to attempt or have an attempt of yourself, and then now we're going to go to a proposed solution for this exercise. So first, we need to import the libraries that we need. So in this case, we're going to use NumPy to use the convolve filter. And also we're going to need matplotlib, which will be used to plot the signals, right? And then first, what we're going to do is we're going to create the signal. So in this case, we are creating a variable called time, and then we create an np.linspace. And then afterward, we're going to create a noisy signal. So here, np.syn is trying to create a signal that is resembling a sine wave, and then at the end, which is the np.random, is trying to create some randomness. So this will resemble the noise in our signal. And then what we do here is we're going to assign the signal data equals to the noisy signal. So this is our initial before any filtering signal. And then we're going to have a plot of the original signal. So this is your standard plt.plot. We give it a title, we give it the axis, we give it the name. So here we're plotting the signal data, which is the original data. And then in step 4, what kind of filter are we going to apply for this exercise? So here we are going to choose a simple moving average filter. And how do we do that? As you can see here, we have in step 5, we are trying to apply a filter to our signal. So if you look here, filtered signal equals to np.convolve. So what we are doing is we are taking the noisy signal and we are trying to convolve it with our filter. And what is our filter? So if you see here, np.ones dot windows in bracket window size, and then we divide it by window size. So this is basically creating a one-dimensional NumPy array with all the elements that are 1. And then afterwards, we're going to divide the whole array with the window size. So the window size is basically a filter that will show how smooth the signal will look like. So here you can say that we have a window size of 10, so that is by default. And then we're going to use our filtered signal with this window size. And then afterwards, we're going to plot the signal after it has been filtered. So it's the same code that we used before to plot the original signal data, but now the original noisy signal, but now we're plotting the filtered signal in addition to the previous signal as well. And then afterwards, let's try to look at how effective this filtering technique is. And then is there any way for us to experiment and try to improve our results? So let's try to run this code. And then here you can see two plots. On the top, you can see the noisy signal, where you have a signal that's resembling the sine wave, but is very erratic and noisy. And then on the bottom, you can see that overlaying the original signal data, we have the filtered signal. And here you can see that it's much less random or much less erratic. And we can see that our filter has some effect onto the signal already. But what happens if we try to change the window size? Do you guys think this is enough? Maybe we need to apply a harsher filter to the data. So let's try to increase it to, let's say, 20, and then run the code again. As you can see, the data is a bit more smooth now. Some might argue this is not enough, or some might say this is enough, but it really depends on what you want to achieve at the end of the day. So this is one way how you can import a data or create your own synthetic data and then apply a filter to manipulate that signal. So this is a proposed solution to this assignment. Of course, there might be other ways, but we hope what you understand from this module is how to manipulate the data that you get and try different methods in your exercises. So that's all for now. Thank you.
So as a next step in our learning of Python, we're gonna try to read the data from external source. And in our case, we're gonna use the library obspy to retrieve the seismic data, the seismograms, and do some operations with that. So in this exercise, we're gonna use determine the velocity of P wave that traveled from an earthquake epicenter to a specific seismic station. So basically, we're gonna take an example of one earthquake with a strong amplitude, and then we're gonna check the data from the nearby seismic station and calculate the seismic velocity that traveled for a specific time. So the main steps here, it will be the data retrieval, so acquire the event, the earthquake, and the station data from the IRIS data center that obspy contains, and then do the visualization, display the seismogram of earthquake of those waves, and then with the ability to select the P wave arrival time. And the next step is going to be the velocity calculation. So basically for calculating arrival time, we need to know the distance between the earthquake and the seismic station, and then the arrival time basically that we're gonna retrieve. And then for the velocity calculation, we use the observed P wave arrival time and the epicentral distance. Okay, and then as a details, we're gonna have this event earthquake, which is the Maule earthquake from Chile, with the magnitude of 8.8. And then as long as we have this event, we know that the earthquake, it happened at the specific time. So it was 2010 at the specific date, specific time. And one specific thing, that's the magnitude. So as long as we have the strong magnitude, we are able to see the changes in the seismic station, and we are sure that such a strong event can have an effect on the seismogram that we're gonna record from the station. And for the seismic station specific, we're gonna use the station from Albuquerque from the US, so we know the location of this seismic station, so we can compute the distance between the earthquake and the seismic station. So the code will work in a way that we're gonna acquire the data from the obspy library. obspy library, that's the open source library. You can check the documentation on their website of the obspy. So they have all the comments and functions, so many that you can retrieve any seismic data, such as earthquake or the readings from the seismic stations, etc. So as long as we have the data, we can retrieve a seismogram, which is basically a time series data that represents the shaking observed at the seismic station for a specific duration around the event time that we're going to use. And then we're going to visualize the seismogram with adjustable red line to identify the P wave arrival time. and that interactive slider that we're gonna use, it will pick the specific time from that seismogram, and it will kind of refer that number to the calculation of velocity. Then we also calculate the epicentral distance calculation, so calculate the distance between the earthquake epicenter that already defined in library, and then the distance to the seismic station from US that I mentioned, and then by itself the velocity calculation. So after we obtain the P-wave arrival time using the interactive seismogram, we can calculate the time taken for the P-wave to travel from the earthquake epicenter to seismic station. So as the first step, you might need to install your library, so OBSpy. I'm not gonna do because it's already installed, so you just need to run this cell. And then as the next step, we're gonna run this cell. So basically what it do, we import all the necessary packages we need. So we import the OBSpy, its clients, its models, the matplotlib library for the plotting, and then we import also the IPY widgets, the widgets that we're gonna use later for adjusting the travel time. So as the first step, we're gonna use the Iris data center. So as the client, the OBSpy library, we use this command, this function, to retrieve the data that we need overall. And then we need to specify the event details for the 2010 Maule earthquake. So here we specify the event time for our seismic station. So we're gonna filter the seismogram that we need for the specific time. And then we also do the we set the magnitude, minimum magnitude here to 8, and then we put the start time and event time to have a specific time range. So for our seismogram, so we will have the seismogram for the time that we need, the same time of the Maule earthquake, kind of with some kind of offset, I would say. And then we assign that data to the variable of origin. The next step is to fetch the data from the seismic station. So OBSpy library has a lot of comments, so we strongly recommend you to check those comments and use them. So here, to define the station that we need, we put the network code, the station code, Albuquerque, and then we put the data that we're going to use to this variable env and est. So we get the station here, basically, the main comment. Here we put our network code and the station code. So this specific function is OBSpy function, so which retrieve the station data. And then specifically, as long as we have the station data, we also retrieve the waveform. So we retrieve the seismogram. We put here the network code, the station code, the location, the channel that we're going to use, that's the specific channel for the seismic, and then the start time and the end time, and we assign it to the TR variable. The next step is to put the latitude and the longitude of our station. So we did it in a way from OBSpy library. So we define its env code variable that we already assigned, so it contains latitude and longitude. So here we do it in a way with the point, and then we choose just the latitude, and the same goes for the longitude. Then the next step is to calculate the epicentrical distance in degrees. So we already have our location of the seismic station. So here we create the new variable distance in degrees. We use the specific function that we already defined. That's for calculating the location in degrees. So we put the origin latitude of our event here. So origin, it contains all the details. Here the latitude, longitude, and then we put the station coordinates as well, latitude and longitude, here that we already defined. Okay, and then we can calculate the theoretical travel time. So for the sake of argument, for example, we can try to get a theoretical model of Earth, and then having those coordinates, we can try to calculate the travel time. So here we're gonna use the Earth model, the tau pi model, which OBSPy has, and then we're gonna assign the arrival time. So we're gonna get the travel times for our earthquake. So we put the source depths from library. So we have this origin depths here. So this variable which has all the details regarding the event, and then we put the distance degrees and the phase list. That's the type of velocities we want to work with. So basically we have the two types of velocities, the primary and secondary. So we're gonna work with primary. And then for theoretical travel time, we also put the first arrivals that we're gonna filter, and then just for the sake of argument, as you can see here, we got a travel time of 713. So basically, then we can check how it works. As the next step, we're gonna visualize the seismogram, and we're gonna use the API widgets. So API widgets, that's the library which allow you to create some tools, interactive tools like sliders, text boxes, and buttons, and many others. So you can kind of filter the data and play with that. So it works in a way that, let's try to run this code, for example. So it works in a way that here we plot our seismogram and we're gonna move this slider. So it works in a way that every time we move the slider, it take the value that we're gonna choose. In our case, that's the time. So it take the time, and then it put that time value to the velocity, for example, formula. And each time we change the slider, it updates the kernel. So every time it will give us the updated values of the velocities. So basically what we do here, we define our functions, which is going to help to visualize. We use the matplotlib, and as we did previously, we basically are using the same functions and commands for example, x labels, y labels. We put our tr times and tr data as x and y values, and then we also print the observed travel time, just to show you how it is. And then as long as we have the travel data, the travel time, we can calculate the velocity. So here, just for the simplicity, we are using also the Earth radius for having more reliable model, I would say. And then simply we calculate the velocity with the distance in meter divided by the observed travel time from the event. So observed travel time from the event, that's the variable that's gonna take the values from that slider from the API widget. So here basically how it works, we are putting the widget's interactive functions. So that's the main tool, the main functions for this interactive tool. So we put our function plot seismogram. So it contains so it will plot the seismogram, and it will take the arrival time. So arrival time is assigned as a widget float slider using the function. So it will change the value and then kind of assign those values each time to arrival time. So here how it works, you change, for example, you take the slider, and to observe the P wave, that's the first arrival. So it should be somewhere maybe here. So we're gonna have around 8,000, and the observed travel time is 1,000. So it's kind of maybe strange values, but it might depend on the different structure of Earth and the different sedimentations. One of the other steps, we can also try to check the secondary wave, this kind of, so it's around 2,000, 3,000. So we need to be careful with this tool, because maybe it should be not that fast. So yeah, it's around 3000. So using the widgets, you can try to play with that and define different travel times and velocities. So try to play with that and read the documentation and run through the code. Thank you for your attention and good luck.